of the orbits of the planets. They are ellipses, and it was discovered by Kepler. Huge amount of work, plotting by hand the trajectories, checking, monster amount of work. If you wanted to do it nowadays with the present technology, it would be a couple of minutes to discover it. And one could argue that the discovery of the orbits of the planet did not harm in any way the development of all the technology that now can be used to discover this. But it was done at a time in which it could be done with huge amount of work. And it's always like this in science. Take also the discovery of the unknown planets. The unknown planets in the solar system, after Jupiter, there was Saturn, there was Uranus, etc. And Neptune and Uranus, they were discovered indirectly by looking at the irregularities of the trajectories of the other planets. Incredible amount of work and hundreds of pages of difficult computation. In those days, they did not have automatic calculators. They did all by hand. Crazy amount of work. A few decades later, it would have been so easier, but it's not the way it was done. People never do the big discoveries when they are easy. They always do it when they are difficult and when they require a lot of work. So, I need to go fast with the rest of the talk. I discussed this at level of individual. Now you can also do all this discussion at the level of organization, like a company. A company works to live and lives to work. They need to have a great plan, which is their goal, which is like we live for this work, but at the same time they need to do something, and usually it's something else to earn their living. Take Google. What was the big art of work of Google? Is make super search engines, things that revolutionize our relation to the internet. This was their grand goal. When they started, they thought they would commercialize this. They would sell this technology. In the end, Google turned out to be the biggest publicity company on earth, doing commercials. They never thought it would do. But that's the thing. They work on the publicity to live, and they live to work, which is improving the search engine. Take Apple. For a lot of time, Apple lived on the Apple II. Not sexy, but was getting money and money. And the big goal was going to the next stage, and it did not, for a long time, it did not work. But they live to work, and they work to live. And in the process, of course, there was the growth, because there is a circle in this. More work implies more life, which implies more work, which gets into more life, and so on and so forth. In mathematical research, also, it's very clear. More and more research, it gives more and more researchers, which have to do more and more research, etc., and so on. And it's like a chain. All this is also part of the culture. Let's conclude it with the last word. All this is social, and in the problem work to live, live to work, one should also think work together, live together, and live together to work together. Because working together for us is also the principal activity that makes bounds or that sometimes exacerbates tensions. Like raising kid for a couple may be the thing that makes the couple close to each other, or on the contrary, the thing on which they separate. But working together is socially very emotional. And this I have seen very strongly in all my activities. Most of my work was done in collaboration. The most important work I did at research level, the one I was telling you about when I was striving with it in Princeton, was done with my collaborator, Clément Mouot. Monster work together. We exchanged hundreds and hundreds of emails, and we were like, during that time, like, brain which was separated into entities, delocalized. One part in Princeton, one part in Paris. this gives bonds forever. And there is nothing that gives stronger bonds than working together on some collective project. I found this again when I did the comics with the graphic artist Baudouin. Enormous work together. For 18 months, we exchanged emails daily about how to represent this and draw this and what should be next, etc. This makes bonds forever also. Better than anything that would be related to enjoying same tastes and so on. Sharing tastes, similar tastes is very important for making bonds, but doing work together is even more important. And that's maybe one of the biggest advantages about science. Science is like a huge collective enterprise in which everybody works together. A similar goal, which is fighting against the unknown. And that's why you have this very strong community sense. I can go in every country, every university, the people there, the scientists there, I will relate to them. They will not consider me as competitors, they will consider me as friends, colleagues, because they know we fought the same fight. And sometimes we are competitors on some paper, whatever, but my work helped this other guy to continue. My work was done in collaboration with this other guy, with this other institution, and so on. It's like a big community in which we all feel we work together, and so we are bound together. And with this idea, I will close my talk. Thank you very much.
You seem to be a person who likes many disciplines, multidisciplinary person. I would personally like to know, how did you personally go about becoming a mathematician? Some personal experiences or motivation or some factors around you which governed your decision?
Okay. So the first, most important advice, if you want to do many things, start by doing one. Start by becoming a specialist in something before you turn to other things. So first become a specialist, get interested. You should always be interested in many things, but you should develop only one subject for a start. It's true in science, it's true in life in general. And once you are really an expert in one subject, it will help you to master other subjects. And when I started my PhD, I was considered a very specialized person, working focused entirely on the regularity of solutions of the spatially homogeneous Boltzmann equation, whatever. A few years later, I was considered very diverse, but I started by being very much specialist. Let me say that I never really had the...
Wiggly as all get out. Now then, when you want to get control of something that wiggles, it's pretty difficult, isn't it? You try and pick up a fish in your hands, and the fish is wiggly and it slips out. What do you do to get hold of the fish? You use a net. And so the net is the basic thing we have for getting hold of the wiggly world. So if you want to get hold of this wiggle, you've got to put a net over it. You see? Now what's going to happen? A net is something regular. And I can number the holes in a net. So many holes up, so many holes across. And if I can number these holes, I can count exactly where each wiggle is in terms of a hole in that net. And that's the beginning of calculus, the art of measuring the world. But in order to do that, I've got to break up the wiggle into bits. I've got to call this a specific bit, and this the next bit of the wiggle, and this the next bit, and this the next bit of the wiggle. And so these bits are things or events. Bits of wiggles, which I mark out in order to talk about the wiggle, in order to measure it, and therefore in order to control it. But in nature, in fact, in the physical world, the wiggle isn't bitted. Like you don't get a cut-up flyer out of an egg. But you have to cut the chicken up in order to eat it. You bite it, but it doesn't come bitten. So the world doesn't come thing, it doesn't come evented. You and I are all as much continuous with the physical universe as a wave is continuous with the ocean. The ocean waves, and the universe peoples. And as the wave, I wave at you and say you. The world is waving at you, at me with you, and saying, hi, I'm here. But we are consciousness, and the way we feel and sense our existence, being based on a myth that we are made, that we are parts, that we are things, our consciousness has been influenced so that each one of us does not feel that. We feel we have been hypnotized, literally hypnotized, by social convention into feeling and sensing that we exist only inside our skins. That we are not the original bang, but just something out on the end of it. And therefore we are scared stiff. My wave is going to disappear. And I'm going to die. And that would be awful. We've got a mythology going now, which is Father Maskell put it. We are nothing but something that happens between the maternity ward and the crematorium. And that's it. And therefore everybody feels unhappy and miserable. No, this is what people really believe today. You may go to church, you may say you believe in this, that, and the other, but you don't. Even Jehovah's Witnesses, who are the most fundamentalists, they're polite when they come round and knock at the door. But if you really believed in Christianity, you would be screaming in the streets. But nobody does. You would be taking full-page ads in the paper every day. You would have the most terrifying television programs. The churches would be going out of their minds if they really believe what they teach. But they don't. They think they ought to believe what they teach. They believe they should believe, but they don't believe it, because what we really believe is the fully automatic model. And that is our basic plausible common sense. You are a fluke. You are a separate event. And you run from the maternity ward to the crematorium, and that's it, baby. That's it. Now, why does anybody think that way? There's no reason to, because it isn't even scientific. It's just a myth. And it's invented by people who wanted to feel a certain way. They want to play a certain game. See, the game of God got embarrassing. The idea of God as the potter, the architect of the universe, is good. It makes you feel that life is, after all, important. There is someone who cares. It has meaning, it has sense, and you are valuable in the eyes of the Father. But after a while, it gets embarrassing. You realize that everything you do is being watched by God. He knows your tiniest, inmost feelings and thoughts, and you say after a while, quit bugging me. I don't want you around. So you become an atheist. Just to get rid of it. Then you feel terrible after that, because you got rid of God, but that means you got rid of yourself. You're just nothing but a machine. And your idea that you're a machine is just a machine too. So if you're a smart kid, you commit suicide. Camus said there is only really one serious philosophical question, which is whether or not to commit suicide. I think there are 4 or 5 serious philosophical questions. The first one is, who started it? The second is, are we going to make it? The third is, where are we going to put it? The fourth is, who's going to clean up? And the fifth, is it serious? but still, should you or not commit suicide? This That was a very convenient theory when the European American world was colonizing the natives everywhere else. And we are the end product of evolution.
Or biquadratic into two biquadratics, or in general any power higher than the second into two powers of like degree. I have discovered a truly remarkable proof, which this margin is too small to contain. Fermat didn't have the benefit of modern algebraic notation, but we do. So let's try to express the idea that a cube can't be written as a sum of two cubes. Well, what is a cube? Well, it's a number like 8. 2 times 2 times 2. That is a product of a number by itself 3 times. For instance, a cube number naturally measures the volume of a cube. It's not just a coincidence we call raising to the third exponent to the third power cubing. Okay, so there we have an algebraic statement, at least of the first thing. So Fermat's first assertion was that it was impossible to find three whole numbers a, b, and c such that a cubed, a times a plus b cubed equals c cubed. And when we're talking about whole numbers, we mean positive numbers, 1, 2, 3, 4, not 0. Suppose we were trying to disprove or show this empirically. Well, we have some props here, and we could do some experiments, right? I have a collection of cubes, right? And so I might be able to take one cube and see if it balances the sum of two cubes. We have a scale here, and we have various cubes lined up. 1 inch by 1 inch by 1 inch. I can't see, I guess you can, so that's one volume. Well, we might imagine that the weight is proportional to volume, so that's how we would use a balance to sort of check things out. Then we have, I guess, a 2 by 2 by 2, which would be a weight 2 inches by 2 inches by 2 inches. So volume 8 and so forth. So let's see if we might just check out with some examples. So some of these look pretty heavy. So what I'm going to start with is one. We have a 6 here, right? 6 cubed, 6 times 6 times 6. So how much should that be? Do we have someone in the audience who's... That's 216, good. And then I'm going to take a 5 cubed. That's 5 times 5 times 5, 125. And that weighs up there. The sum is 341. And let's see, suppose we want to prove Fermat. So I take a 7. 7 times 7 times 7 is what? Almost, right? 3. So we had the sum there was what? 341. And now 343. Let's see whether... Oops. Almost, but not quite. So if I was an experimental mathematician, at least I didn't find a counterexample yet. So it's close but not exact. And Fermat was saying that no matter how hard one tries, it would be impossible to find two cubes of whole number sides that balance another cube with a whole number side. And Fermat asserts more generally the impossibility holds for all larger exponents. This is the more general statement. And notice, to show that Fermat is wrong, all you have to do is find a single example of whole numbers a, b, and c, and n greater than 2 that satisfy this equation. Although many people have tried, no one has found a solution n bigger than 2, and now Andrew Wiles says that no one ever will. It's impossible to know what was going on in Fermat's mind. The only proof of Fermat that we know is the proof of his theorem n equals 4, and by an ingenious argument using a technique called infinite descent. It's sort of a technique by showing if you have one example, you can get a lower one, and a lower one, and a lower one. He showed that the equation a to the 4th plus b to the 4th equals c to the 4th is impossible in whole numbers. He refers to the cases n equals 3 and n equals 4 frequently in his subsequent correspondence, but never returns to the general case. More than 100 years later, the Swiss mathematician Euler, who spent much of his time in Russia, gave a proof of Fermat for n equals 3. Fermat's seemingly innocent remark has led to an enormous amount of mathematics, although number theory was regarded almost as a recreational endeavor in Fermat and Euler's time. By the early 1800s, the deep work of the German mathematician Carl Friedrich Gauss gave number theory respectability and importance that it retains to this day. By the middle of the century, Fermat's statement has become known as Fermat's last theorem because it was the last of Fermat's assertions that remained unsettled, not because it was the last one that he ever stated. Gauss, perhaps the greatest mathematician of all time, felt that the question had little importance in itself, but was instead the tip of an iceberg of a far larger mathematical domain. In 1860, the French Academy offered a prize for work on Fermat's last theorem, and this led to a flurry of activity that, again, has continued unabated to this day. Some of the first general work on Fermat's last theorem was done by Sophie Germain. Germain was the first to make progress for a large class of n's at once. So up to this time, it had only been shown for particular numbers, in particular 3 and 4, and Sophie starts looking at a more general, takes a more general approach. And to give a sense of what it was like to be a woman interested in mathematics at the time, it is perhaps worth taking a few minutes to tell a little bit about this remarkable woman, so I'll digress for a minute or two. Sophie Germain was born in Paris in 1776, the year of American independence, and was a young girl during the French Revolution. For protection, she was kept at home. Starved for mental stimulation, young Sophie began to read math books in the family library, and this became a passion with her. Her family vehemently disapproved of such studious tendencies and, concerned for her mental well-being, took desperate measures. They denied her light and heat for her bedroom in order to force her to sleep at night instead of to study. But after Sophie's parents were asleep, she would wrap herself up in quilts, take out a store of hidden candles, and work all night. After finding her asleep at the desk in the morning with ink frozen and calculations on her slate, her family finally relented. By the time Sophie Germain was 18, Paris was settling back to normal, and the École Polytechnique was founded. Although women were not accepted, Sophie Germain collected lecture notes of various professors and started communicating with mathematicians using the pen name Monsieur Leblanc, so they would take her seriously. In 1804, after reading Gauss's Disquisitiones, Monsieur Leblanc began a lengthy correspondence with Gauss. It was not until 1807 that Gauss discovered her true identity. He remarked that the question of gender mattered little to him, and let me read to you a few lines from his letter to her at that time. But how to describe to you my admiration and astonishment at seeing my esteemed correspondent, Monsieur Leblanc, metamorphose himself into this illustrious personage who gives such a brilliant example of what I would find difficult to believe. Apparently she had sent him a theorem. A taste for the abstract science in general, and above all, the mysteries of numbers, is excessively rare. It is not a subject which strikes everyone. But when a person of the sex which, according to our customs and prejudices, must encounter infinitely more difficulties than men to familiarize herself with these sorting